All right, how's it going, Math 1? This is lesson 3.4, Solving Special Systems. This is our last lesson in the chapter, and we are finishing up our Systems of Equations unit in Khan Academy. This lesson covers skills 11, 12, and 14. So far, in 3.1, 3.2, and 3.3, we have seen different ways to solve linear systems of equations. In 3.1, we saw graphing. In 3.2, we did substitution. And in 3.3, we saw elimination. Excuse me. But so far, I've given you nice systems that have one solution. And that's not always the case. Sometimes weird things happen. And here is our first example of that. So we have a system, and we want to solve it by graphing. So I'm just going to sketch a graph here. We'll draw our x-axis and our y-axis and our x-axis. There we go. And I notice that the y-intercepts are -4 and 2. So I need to make sure my tick marks on my graph show at least that. So there's -4, and I'll put a couple more. And there's 2. I'll put a few more. I'm not sure how many x-axis tick marks I'll need, but that should be enough. And then let's graph our lines. So here's our first equation. I'll graph it in blue. Our starting point is going to be our y-intercept at -4. And then for my slope, I'm going to go up 1 and over 2 and put a point, right? So let's do that. And I could just draw my line now. If you want to be a little more precise, you could do it again. Go up 1 and over 2. Or you could go down 1 to the left 2. Either way, we'll get a graph. Oh, that's not what I want. It should go through the dots. Hopefully your line is straighter than mine, but you get the idea. There's our second equation. It starts up at 2 on the y-axis. And then, it has the same slope. So I'm going to go up 1 and over 2 again. And I should have a line something like this. And these lines are going up. They're increasing at the same constant rate. They have the same slope. And this is a really important vocabulary word. You should write this down. Parallel lines, they have the same slope. They don't intersect. Do not intersect. And if you remember from 3.1, our solution was that point where the lines crossed. These lines aren't going to cross, so there's no solution. You don't have to know this, but sometimes they put this symbol on the lines to show that they're parallel. But yeah, these lines are parallel. They don't cross. Let's try it with number 2. We're going to do the same thing. It's just these equations aren't in slope-intercept form yet. So let's take this first equation that was given to us in standard form, and we're just going to switch it to slope-intercept form. The first thing I could do is subtract 5x from both sides. And if I subtracted 5x from the left side, I just have 3y on the left. And then on the right side, I could write 6 minus 5x. I'm going to put the x term first. So it'll say -5x plus 6. That way it's closer to being in slope-intercept form. And then if we divide both sides by 3, I'd get y equals -5/3 x plus 6 divided by 3 is 2. And so that would be our first equation written in slope-intercept form. All right, and then our second equation, really it's just that 3 in front of the y that's messing it up. So let's divide both sides by 3. 3y divided by 3 is just y. And then, again, I'm going to divide both terms on the right side by 3. And I'll get -5/3 x minus 1. And we should notice, even at this point, the slope is the same in both equations. Okay, but it looks like they have different y-intercepts. So let's graph those. Here's our x-axis, our y-axis. Now, as I'm making these tick marks, there we go. You should notice that the y-intercepts, they're not very big. They're 2 and -1, but I put more tick marks than that on the y-axis because our slope is going to be a little steeper. So let's go to 2 on the y-axis for our green line, and we're going to go down 5, 1, 2, 3, 4, 5, and over 3. So we'll have a line that looks something like this. And then for our purple line, same slope, but it starts down here at -1, and if I go down 5 and 5 and then over 3, it should put me about, it should put me about here. And we have parallel lines again. They're parallel, and we noticed that because their slope was the same, but this is just confirming that. So no solution. We should say no solution. All right. Before I talk about this this nice picture here, I'm going to draw that again for you in a moment. I want to quickly recap what we've gone over so far this semester. You don't have to write this part if you don't want to. It might be nice, but I want to limit what you actually have to write down in your notes. So if you want to set your pencil down and just follow along for a moment, that's fine. So in chapter 2, all the way back in chapter 2, you learned how to graph a line. So I gave you an equation like y equals mx plus b, and then maybe the graph looks something like this. Now, any point on this blue line, maybe this point here, you can think of that point as an ordered pair, x comma y, and x and y in the equation, those are variables, so they can take on different values. They vary, right? But if I were to take this point and plug those coordinates into the equation, because that point is on the line, we should get a true statement. Because m and b are just numbers, right? So we can multiply m times x, add b, and we should get whatever the y coordinate was. We should get a true statement in the end, like 5 equals 5 or 3 equals 3. And that should also work if I picked a different point on the line, any point. A line is really a collection of infinitely many points, and any of these points should make this equation true. We should get a true statement if we plug those coordinates in, all right? But then we got to chapter 3, and now I'm having you graph 2 lines. So maybe the first line looked like that, but the second line looked like that. And so any point on the blue line satisfies the equation y equals mx plus b, right? For whatever m and b are. But the red line is different. It has a different slope. It has a different y-intercept. So let's say it's y equals nx plus c. We don't really use n and c often. I just changed the letters because I want to show that the slopes and y-intercepts are different for these two lines, okay? But in chapter 3.1, we found where those 2 points cross. And the reason that purple dot is considered a solution to the system is because it's on the blue line and it's on the red line. So if we plug those in, if we plug this xy coordinate into the blue equation, it's on the blue line, so we'll get a true statement. But it's also on the red line. So if we plugged it into this equation, we should also get a true statement. They might be different true statements. We might get 3 equals 3 here and -5 equals -5 here or something like that. But the fact is it makes both equations true. This point satisfies both equations. Okay, so if you did set your pencil down, go ahead and pick it back up. Now we can keep taking our notes. This picture looks just like what I drew in the margin there. That point of intersection, there's only one point of intersection, and that's our solution. The lines that intersect, they have different slopes. We have one solution. But you just saw in the two examples above, some lines don't intersect at all. Since there's no point of intersection, there's no solution. And in this case, the lines are parallel, and that means they have the same slope. But I call it, they're distinct parallel lines because they also have different y-intercepts. They're not the same line, okay? The third case, I think this picture looks a little bit confusing at first because it looks like one line, but it's actually saying that, well, we took our first equation and we graphed it, and then we graphed the second equation, and it happens to be the same line graphed on top of itself. So in that case, when we're looking for a point of intersection, a point that's on the blue line and the red line, every single point on the blue line is also a point on the red line, right? So that's why we say there's infinitely many solutions. It does not mean that everything is a solution, right? Because obviously, like this point down here, isn't on the blue line or the red line. That's not a solution. But there are infinitely many purple dots that I could put on this graph. This arrow means it goes on forever. There's infinitely many points that are on both the blue line and the red line, and that's why there's infinitely many solutions. They're the same line, same slope, and same y-intercept. Okay, so that's how to identify these kinds of special systems or weird things by graphing. You should also know, actually, before we move on, let's do some on your own. So try 3 and 4, get them in slope-intercept form, graph them, and you tell me, is there one solution, no solution, infinitely many solutions? And after you do that, come back and check your work. Okay, so for number 3, I put a blue check mark here because I'm going to graph this equation in blue, but it's already in slope-intercept form. The second equation is not, so let's get it in slope-intercept form. And when you have them in slope-intercept form, we notice that they have the same slope of 3, but they have a different y-intercept. So even without graphing, since they're in slope-intercept form, we know that they have the same slope and different y-intercepts, so they're going to be parallel. But there's a graph of it. Your lines hopefully look a little more parallel than mine. They look like they kind of go away from each other there, but they are parallel. So, oh, I forgot the most important part. They're parallel, so we should say there's no solution. All right. And then number 4, same thing. The first equation is already in slope-intercept form, but the second equation is not. So we get it in slope-intercept form, and we find that they have the same slope, but this time they also have the same y-intercept. So we end up having the same line graphed on top of itself, and so we say they are infinitely many solutions. Every point on the purple line is also a point on the red line. Okay, so that's graphing. Now let's take a look at how can we identify these special situations, these weird things that happen if we're using substitution or elimination. So number 5, we are substituting. And remember, for substitution, you want to get one variable by itself. We already have that. Since y equals 8x minus 1, I'm going to take 8x minus 1 and plug it in for y in the first equation. And when you substitute, make sure you put parentheses around the thing you're substituting in so that you remember to distribute. And we'll get that. And now we can combine like terms and try to solve for x. But the x terms end up canceling this time. So there's no x terms anymore, the variable goes away, and we get a true statement. We get that negative 2 equals negative 2. And if you get a true statement, whether you're substituting or eliminating, that is the same thing as having one line graphed on top of itself. There are infinitely many solutions. Okay, Let's try the elimination method. Remember, for elimination, you want to line up your x's, line up your y's, line up your equal signs, and then line up the constants on the other side of the equal sign. We already have that, but the x coefficients are not opposites, and neither are the y's. I'm going to try to cancel the x coefficients. So I'm going to multiply both sides of the second equation by 6 so that I get an 18x to cancel out that negative 18x. So there's the first equation just rewritten. There's the second equation after I multiply both sides by 6. And then I can add the terms, add the both sides of the equal sign, really. But unlike what you saw in 3.3, remember how I was trying to cancel out the x's? And I got that, but it just so happens that the y's cancel out as well. I still have to add the numbers on the right side. I get 12. And this is false. 0 is not equal to 12. So if you get a false statement, that's when there's no solution. This is the equivalent to graphing two distinct parallel lines. They never cross, there's no solution. And then here is a table just to sum up what you've learned so far in this lesson. So if you're graphing, then these are the 3 cases. You could either have parallel lines that never cross, you could have lines that intersect once, and then there's one point, one solution, or you could have the same line graphed on top of itself, and every point on the first line is also a point on the second line, and that would be when there's no solution, one solution, or infinitely many solutions, respectively. Okay? And then if we're not graphing, if we're using a more algebraic method like substitution or elimination, then if the variables cancel and the sides are not equal, you get something like 0 equals 3, or obviously that's not really true. That's when there's no solution. Or you have plenty of examples of one solution in lessons 3.2 and 3.3, but if each variable has one solution, let's say you end up with, x equals 5, and then you plug that into an equation and you get y equals something else, then you have one solution, right? That solution would be the ordered pair 5, 2. But sometimes the variables cancel and the sides are equal. You get something like 7 equals 7 or whatever. If that's the case, that's when there's infinitely many solutions. Anyway, that's it for lesson 3.4. This is our last lesson in the chapter, so get ready for your study guide and test. As always, ask a question at the end of the video or make up your own, and I will see you all in class.